Hi everyone, in this video we will cover some basic meshing information with respect to structural simulations. So we will start by comparing 1D, 2D and 3D meshing, then we will cover some essential mesh setting to consider, and we will finish with a short demo. In general, any real-world objects can be modeled with line surface of solid bodies. So line body will be used for slender body, where the thickness or any other lateral dimension is kept small when compared to its length. The body must also have a constant cross-section. In ANSYS, many element type exist to model line bodies. So we have links element that can be used to model truss structures that supports only tension and compression load. A beam element can be used to model frame structure that will also support bending and torsion. Cable are similar to the link element, except that they are very suitable for very slender cable structure. And finally, a pipe element can be used and are very similar to the beam element, and the pipe will support inner and external pressure as well as temperature. For the surface body, they are divided into two categories. So the 2D body can be used to model thin planar structure using a plane stress assumption, infinitely long structure having a constant cross-section based on a plane strain assumption, or axisymmetric structure. We also have 3D bodies that are used to model thin to moderately thick structure, both flat and curved. And the element type associated with the 2D bodies are the plane, and the element type associated with the 3D bodies are the shell. Finally, a solid body will be used to model any kind of geometry that doesn't fall into the two above categories, and it's basically used to model like thick structure in a 3D space. Most of the time, the element type that we will use for solid body is going to be the solid. And in ANSYS, we will most of the time again use either an hexahedral or a tetrahedral element shape to model the solid element. On this slide, I simply want to depict some different geometry representation of the same H-beam. So from left to right, we can start with the line body. So this is a line body representation of the H-beam using a beam element type. Note that the cross-section and moments of inertia will be considered in the equilibrium equations, but they are not part of the geometry. So here in the space claim, I turned on the solid beam displays only to show the beam profile in orientation, because in reality, we only have a single line body. In the center, the H-beam is represented using three surface bodies, modeled as a shell element type. Similar to the beam element, the thickness of each surface will be considered in the equilibrium equation, so they are not, again, part of the geometry. And here again in space claim, we have turned on the thick shell display, here only to show the thickness of each surface, because again, in reality, we simply have a surface body, three surface bodies inside space claim. Also note for the surface body that using this approach for this specific geometry, we were not able to model the fillet like we did for the solid body. So on the right, the solid body representation, we will either use hexahedron or tetrahedron finite element to discretize the geometry, and you can see this method as the simplest way to model a part, but this will often lead to more equations to solve in the model. If we compare the structural response of these three different representations of the H-beam using a cantilever setup, which is a fixed support here on the right and a uniformly distributed load on the top of the beam, we can see that from left to right, the number of nodes, which is proportional to the number of equations to solve, is increasing. So for the line body, we have approximately 50 nodes. Surface body, we are now at 8,000, and the solid body, we are at 350,000 nodes. However, the max total deformation doesn't really change from a model to another. So the only reason why we got more deflection on the surface body is that because the fillets could not be included in the model, which led to a more compliant structure. But overall, we got the same answer, and a significant amount of node was required for the solid and the surface model when compared to the line model. And in this specific case, the line model should be favored over the two other because there are no added value if we are only interested in the total deformation. So now let's talk more about meshing. So first, the fundamental purpose of meshing is to discretize the domain into finite element, and then to solve all the equilibrium equations of the system to get the degrees of freedom for each nodal location, which can be displacement for structural simulation or temperature for thermal simulation. Efficiency, accuracy, and quality are among the mesh requirements. So you can see, for example, accuracy as a way to get some result that won't be dependent of the mesh size or any settings, for example. For the efficiency, basically we want to get a solution within a reasonable amount of computing time. So to get a good trade-off between efficiency and accuracy, we will most likely refine the mesh near high solution gradient, such as stress, and we will use a coarser element size elsewhere. As for the third requirement, the mesh quality, this one is very important because sometimes a solution may fail to converge in a nonlinear analysis due to a poor mesh quality. We can have a look at the element quality if under the details of mesh we change the display style to element quality right here. Finally, to get an efficient, accurate, and high quality mesh, we will most likely need to control the global and local mesh settings, which are available here on the right. So the global settings will be available in the details of the mesh here, and you will have access to a lot of local control setting in this drop-down menu. Finally, the mesh settings is also physics dependent. So whether you are doing a structural, electromagnetic, or CFD simulation, the mesh setting will be different. In this slide, we want to discuss a bit more about 3D solid element shape because 3D solid elements are used most of the time. And like mentioned previously, most solid body can be discretized either into hexahedral or tetrahedral element shape. An hexahedron has 8 vertices, 12 edges, and it is bounded by 6 quadrilateral faces, while a tetrahedron has 4 vertices, 6 edges, and is bounded by 4 triangular faces. In general, hexahedron elements are more efficient when compared to tetrahedron because less elements are required to mesh the same domain. And this will consequently lead to a faster solution time. And also hexahedron elements are more accurate. However, not every domain can be meshed with a hexahedron element. So this depends a lot on the complexity of the geometry. So this is why sometimes you will have to use tetrahedron mesh because this mesh method is the most robust to model complex geometry. For the element order, we have the choice between linear and quadratic elements. The difference between the two is that mid-size nodes are added to the quadratic element. This will generally lead to a better accuracy when compared to the linear element. However, a linear element, if properly used, will often yield to an acceptable and accurate solution within a reasonable amount of computing time. Basically, inside mechanical, if you go on the details of the mesh, you can choose the order here between linear and quadratic. Also, if you will be using a linear element, you should avoid using lower order tetrahedron or triangle. Furthermore, for most non-linear simulations, such as thermal and magnetic simulations, the linear element will lead to an excellent trade-off between accuracy and computing time. So like I'd mentioned, quadratic elements are better than linear, but sometimes the difference is very subtle. So like you can see in this schematic representation of a mesh sensitivity study, linear and quadratic hexahedron element will often lead to very similar results. However, we definitely need to consider quadratic element for tetrahedron and triangle, and also with degenerated element shape. So in the next video, we will simply go over a demo of a water tank where we will combine all sort of element type, and we will also discuss a bit about the mesh control. Thank you.